So in the 1980s, 90s, and even early 2000s, one of the biggest problems with neural networks has been this problem of vanishing gradients. This is the reason, literally, this is probably one of the most important reasons why people lost interest in neural networks in the late 90s and early 2000s. This is not the only reason, but it's one of the important reasons. Vanishing gradients is a so remember all of your functions earlier, right? So all of your Fijs, people typically tried sigmoid. People typically tried sigmoid units as your activation units earlier, right? This is because all your Fijs are sigmoids. There is one problem, or tanh, right? There is one major problem with sigmoid, which is also the same problem with tanh. And the most popular activation functions that you had in Fijs were all sigmoids then. So let me explain the problem. Suppose if I want to update this weight W111, right? This is my standard network that we have been seeing till now. So if you look at this network, and if what is the derivative of L? Because if to update this weight, to update W11 new, right, you need W111 old in each iteration minus eta times the derivative of L with respect to this, right? And the most important part of this was this computation, right? So the derivative of L with respect to W111, right? You can write this as, again, we derived this in one of the previous videos, but I'll quickly show it to you. This 111 impacts O11. This O11 impacts O21. So it has this path, right? It has this path, which impacts your loss function. It also has this path, which impacts your loss function. So I can quickly write this as derivative of L with respect to O31, because O31 is nothing but my yi hat, multiplied by derivative of O31 with respect to O21 multiplied by derivative of O21 with respect to O11 multiplied by derivative of O11 with respect to W111. I'm just doing this path. We have seen how to compute this. Plus, sorry, I should close the braces here. Plus, there is also the second path, right? Plus derivative of O31 with respect to O22, derivative of O22 with respect to O11, derivative of O11 with respect to W11. Right? Because we have two paths here. Because this weight influences O11. O11 goes and influences your loss function this way and this way. There are two paths, right? So if you notice in these whole derivatives, right? Let's look at it. This is O31 is basically an output of your function. It's basically an output of your function, right? Remember, what is O31? O31 is basically applying F31 on the inputs that you get, right? So derivative of O31, with respect to O21 is nothing but the derivative of F31 with respect to O21, because O31 is nothing but the output that F31 is generating, right? And remember, each of these functions are sigmoid. Which means these derivatives, as we saw in the previous video, the derivative of F31 with respect to O21, because this is sigmoid, lies between 0 and 1. In the case, it lies between 0 and 1, right? So if you notice, this value lies between 0 and 1. Or strictly speaking, this value lies between 0 and 1. This value also lies between 0 and 1. This value also lies between 0 and 1. This value is also between 0 and 1. This also is less than 1 and greater than 0, of course, less than 1. Now, if you have multiple numbers, look at these three. These three are being multiplied, right? If you look at this, these three values are less than 1. You're multiplying them and you're adding it to some other set of numbers or group of numbers which are all less than 1. Let's only focus on the first part here. Let's focus on this part. You have three numbers, all of them less than 1. So what happens in such a case? In such a case, one fun thing could happen, right? So what you have here is the derivative of O31 with respect to, let's just focus on this first part here. Let's just focus on this first part because it's a multiplication, which is the most important thing for us. Okay, so that part is O31, derivative of O21 with respect to O11, derivative of O11 with respect to W11. Now this value is less than 1. In the case of sigmoid, it's less than 0.3 actually. So let's assume this value is 0.2. This value, let's say, is 0.1. This value, let's say, is 0.05. And you're multiplying all of them. When you multiply these three numbers, what do you get? Right? You get you get 10 here, the multiplication of both of them. You get 1, 2, 3, 4, 4 decimals. You get this value. You get a value which is much smaller than any of these gradients. Look at this. This is 10 power minus 3. Because you're multiplying numbers all of which less than 1, this is less than 1, this is less than 1, this is less than 1. Because you're multiplying numbers which are less than 1, the value that you get is significantly less than 1. It becomes a very, very small, minuscule value. Right? And remember, you are using this minuscule value in the update function. So this update, because this product is again being used to compute this. And this is what is this? This is what is going into your update equation. Right? What is your update equation? Your update equation is W111 new equals to W111 old minus eta times the derivative of L with respect to W111. If this product is small, see, this product becomes very small, right? Then what happens if this product is small? This product is also small. You're adding two small values, doesn't change something big. But this overall derivative that you have also becomes very small. So this overall derivative that you have here, so this is very small. So each of these are small. Multiplying very small values which are all less than 1 makes it very small. So this derivative becomes very small. When the derivative becomes very small, your W11 new, let's assume this value is 0.001. And let's assume eta equals to 1. Let's just say eta equals to 1, just for simplicity. Okay, and this value is very small. Okay, let's assume your older weight is 2.5. Sorry, your older weight, sorry, not the new weight. Your older weight is, let's say, 2.5. Then what happens in this iteration? You have 2.5 minus 1 multiplied by 0.001, which is 2.5 minus 0.001, which is 2.499. So your new weight here becomes 2.499, which is very, very close to your old value. Your new weight is very, very close to your old value. Because your derivatives are small. Why are your derivatives small? Because each of your individual derivatives that you're multiplying as part of chain rule are less than 1. Right? And why are these less than 1? Because of sigmoid. Because of sigmoid activation. You understand the logic here? Okay, let me repeat it. Okay. So your new weight is very close to the old weight because your derivative of the loss function with respect to the weight is very small. And why is it small? Because this is computed using the product of other derivatives where each of these derivatives is less than 1. When you multiply multiple values which are less than 1, the final value that you get is very, very small or very small. And why are these derivatives small? Because of sigmoid and tan h. In other words, because you have your activation functions as sigmoid or tan h, your update or you're updating the weight becomes very, very hard. Right? And remember, to do this, you've computed all of these derivatives, multiplied, added all of that. And this is just 3 layers. Remember, this is just 3-layer network. You have basically 2 hidden layers, 1 input layer and 1 output layer. Imagine instead of 2 hidden layers, let's say you have 10 hidden layers. Because I have 2 hidden layers, I'm multiplying these 3 values. Imagine if I have 10 hidden layers, I would have 11 such multiplications. I would have had 11 such multiplications, right? So the number of multiplications, so the number of multiplications of derivatives is number of hidden layers plus 1. So when I had 2 hidden layers, I was multiplying 3 derivatives, like in this case, to update the weight in this layer, because there are 3 layers ahead of me. Right? In the first layer, just the points, the weights that are connecting the input layer to the first layer. To update this, I'm doing 3 multiplications. Imagine if I had a 10-layer network or 10 hidden layers, then I would have had to do 11 multiplications. If just with three multiplications of values less than 1, I got a very small value, right? I got a value which is 10 power minus 3, right? In this example, in this simple example. What happens if I have 11 layers? This value becomes like 10 power minus 15 or 10 power 20. Very, very small value. This is like very, very, very small. If this is very small, right? This product, the the product of the multiplication of derivatives, right? Through chain rule. We are multiplying them because of chain rule, right? Because of chain rule, we are multiplying them. Now with 3 layers, if the derivative becomes this small, with 11 layers, it can become much smaller. Like this will be at least 10 power minus 10 or something, right? And if this derivative becomes smaller and smaller, my newer weight and older weight tends to become almost the same. Imagine if this derivative was, instead of 10 power minus 3, if it was 10 power minus 10, then my new weight would have been 2.49999999 and my old weight would have been 2.5, right? Which is exactly almost the same thing. It looks like a rounding error to me. So when you have this problem, so this problem is called vanishing gradients. Why? Because the final gradient that you're getting here, is vanishing, or it's becoming very, very small or very small because of this chain rule based multiplication, right? So in a nutshell, vanishing gradient basically means that the derivative that you have with respect to some of the weights w, I, j, k, this derivative is becoming very, very small. And why is it becoming very, very small? Because of your chain rule and multiplication of derivatives. And this multiplication of derivatives, each value being less than 1. And this is less than 1 because you're using a sigmoid or a tan H activation, right? And when you have the vanishing gradient, what happens? Your new values, w, I, j, k, new becomes very, very similar to w, I, j, k, old. Which means you are not updating your old values to new values much. Because of all of this is because of the sigmoid or tan H activation. Or one of the biggest problems is not just because of this, one of the biggest problems is because of the sigmoid and tan H activation, right? So now this whole thing puts the whole approach of backpropagation into jeopardy. And we know no other technique to actually train neural networks. So vanishing gradients created this huge problem in the 80s, 90s, even in the early 2000s, because people could not train deeper networks. People could train maybe 2-layer networks, two hidden layers. 2 hidden layers was the maximum that people were training. People could not train 5 hidden layers or 10 hidden layers or 20 hidden layers. This was just impossible, completely impossible to do because of vanishing gradients. Because when you have 5, 10, 20 layers, your weights in the first initial layers do not change at all. They simply get stuck wherever they have been initialized, right? So building truly deep neural networks. Deep basically means that you have lots of layers. A 20-layer network is called a deep neural network. A 2-layer is like okay. It's okay. It's slightly better than probably a logistic regression. But your brain, people knew from biology that actually human brains had tens, even hundreds of layers of depth in some cases, right? So to really mimic the human biological structure, the structure of our brain, people said, I have to train deep neural networks. But they couldn't train deep neural networks because of the vanishing gradient problem, right? We will see how to, and remember, one of the biggest reasons for vanishing gradient problem is your sigmoid and tan H. The whole reason why ReLU activation units were discovered or they were created was to get rid of the vanishing gradient problem. We will discuss the ReLU activation unit in the next chapter in lot of detail, right? So this is one of the reasons. The next thing that, okay, just the way we have seen vanishing gradient, there is a related problem called exploding gradient. There is a related problem called exploding gradient. We will encounter exploding gradient more often in one type of neural networks called recurrent neural networks. We will come to recurrent neural networks a couple of chapters down the line. But I just, because we've anyway discussed vanishing gradient, we'll also discuss exploding gradient for completeness. So what is vanishing gradient? Vanishing gradient basically means that your derivative of L with respect to any weight becomes very small or very, very small. This is a problem of vanishing gradient. What is the problem of exploding gradient? Exploding gradient is the exact opposite problem. Your derivative of loss function with respect to, or partial derivative, sorry, or partial derivative of it with respect to some weight becomes very, very large. If it becomes very, very large, that's also dangerous. Let me explain why. Because if I have a weight like this, Wij new equals to Wij old minus eta times the derivative of, the partial derivative of L with respect to this. This is what I have here, right? Now, if this is very small, what happened? Your older value and newer value were roughly the same. But imagine if this becomes very large or very, very large, then what happens? Your Wkij old is very, very different from Wij new. Because this is a large value, you're subtracting, so let's assume your learning rate is 1, just for simplicity. Okay, just let's make this 1. Then what happens? Because this value is very large, your old value and new value change a lot, right? Which is okay in the initial stages. But what happens is, let's assume I'm running iteration 1, iteration 2, iteration 3, iteration 4, iteration 5, iteration 6, etc. What happens is, from one iteration to other iteration, my weights will change so much. My weights will change massively. What do you want to happen? Ideally, as we saw in the optimization chapter, as we go from one iteration to other iteration, right, the difference between these two values will keep shrinking till the time you converge to the solution. But what happens is, because you have a large derivative, right, there is a large difference between your weight Wkij in second iteration and first iteration. Instead of saying old and new, let me put the iteration numbers here. Okay, so you have your Wkij1, which means at the end of iteration 1, you have Wkij at the end of iteration 2, you have Wkij at the end of iteration 3, so on and so forth. What happens is, even after, let's say, 10 iterations or 20 iterations, right? Even after 20 iterations, because this derivative value is large, what happens? You will never converge literally. Because even this gap, even after 20, 50, 100 iterations, you will not converge because it keeps changing. Because this derivative keeps changing. It's a large value. Right? When it becomes a large value, you will never converge. So you don't know where to stop. And your weights will change dramatically in all sorts of directions. Initially, your weight may be 2.2. Then your weight may become 10.8. Then your weight may become 100.6. Right? Then your weight may become 1,000. Then your weight may become 1 million. There is no control over it. Right? There is simply no control over it, or it can become, so when your derivative is very large or very small, very, very small, very, very large in a negative sense, that's what I meant. Sorry, not small. Apologies, not small. So if it is, let's say, 100, or if it is, let's say, minus 100, these are large values, right? So if the absolute value of your derivative is very large, that's what I meant, not small. If you have small, you have the vanishing gradient problem. In the case of exploding gradient, if this value becomes very large positive value or very large negative value, then you run into the exploding gradient problem. Because this minus sign just becomes plus if it is a negative value, that's it, right? Right? This minus, if I multiply with minus 100, becomes plus 100 instead of minus 100, except that nothing else changes. Now you may wonder, why does exploding gradient occur? Why does exploding gradient occur? Again, it occurs for the same chain rule. Because of chain rule, right, you are multiplying lots of derivatives. Imagine that each of the derivatives Okay, let's look at this. The derivative of L with respect to W111 is, okay, in the computation of this, we had this unit, right? Derivative of O31 with respect to O21, sorry, with respect to O21 multiplied by derivative of O21 with respect to O11, derivative of O11 with respect to W111. So when all these values were small, we had the vanishing gradient. Now imagine if each of these values is greater than 1. That doesn't happen in the sigmoid units as much, because the sigmoid derivative itself, right? The sigmoid derivative is less than 1. But imagine we had some function. Suppose we had some activation function. Suppose we had some activation function which is resulting in these derivatives becoming greater than 1. Right? When you have lots of values which are greater than 1, when you multiply them, let's assume this is 2, this is 2, this is 2. Even though each of these values are 2, when you multiply all of them, you get 8, which is a significantly larger value than 2. Right? So if you have activation function or situations, we will see some situations when we learn recurrent neural networks where we often find this problem of exploding gradients. Right? So if you ever come into a situation where you have your gradients greater than 1, right, where you have your activation units with gradients greater than 1, the overall product of all of them can become extremely large, which means your derivative can become extremely large, and when your derivative becomes very large, your update becomes large, which means you can't converge. So typically, exploding gradient problem occurs if your derivatives are greater than 1, because in chain rule you multiply, right, which creates the exploding gradient problem. And with exploding gradient problem, your weights do not converge. Weights do not converge, and they keep changing, and they keep changing erratically, like crazy, literally. Right? That's what is the exploding gradient problem. This is the reason why we have the exploding gradient problem, and these are the repercussions of the exploding gradient problem. Right? We will see exploding gradient in more detail when we learn recurrent neural networks.